Alright, today we're talking about Chapter 5, Section 3, the properties of logarithms. So now we're going to, we've learned what logarithms are. Now what we're going to do is figure out how to manipulate them algebraically. Okay, I don't really like that there. Alright, so this is our properties of logarithms. This in the blue box is what we're more focused on. Right, and these work both forward and backwards. So what I mean by that is, and let's just start with the first one. If we have some log base b of u times v, then we would be expanding the logarithm by basically splitting up that u and that v. So notice how, that everything's the same, log base b, log base b, log base b, everything's the same. It's just that the u and the v are split up. Okay. Now the u and the v are split up by an addition sign because we are multiplying. Okay. And as you would expect, excuse me, as you would expect, the u and the v is split up by a subtraction sign if we are dividing. And we'll talk about those two a little bit more right now instead of going to the third one. So I said that going from left to right there is expanding, okay? Well, if we were to go from right to left, right? So if we were given a problem like this, and we were told to condense it, we would turn the logarithm into that, okay? From right to the left side. So in this particular definition, we are expanding going from left to right and condensing going from right to left, okay? And again, multiplication is addition and division is subtraction. Okay, we've seen that before. And then lastly, the power rule. Okay, the power rule, right, notice how we have some log base b of u, okay, and it's raised to some r power, all right? Well, what we do with that r is we put it out in front, right out front, okay? And that's it. That is the power rule. We just take that exponent and put it in front of the entire problem. Pretty easy, pretty fun. And again, I hate to reiterate this, but we're in the part of the mathematics where it's just a lot more fun, and we just move things around instead of the mindless computation. Now, that's not to say that there won't be, but I'm just saying that this is the beginning of more fun stuff to me. Just in time for the semester to end, right? Alrighty, so example 1 reads, use the product rule for logarithms to expand. Okay, so we're going to be expanding. So we're looking at this definition, and to expand, we're going from left to right. Okay, and that's very obvious when you actually even look at the problem, right? It's obviously very, very condensed there. Okay. All right, so A, we have natural log of 5x. Okay. Well, we are multiplying the 5 and the x, right? So it's essentially looks something like this. 5 times x, right? That's what it looks like. Well, we know that if we are multiplying, we can put an addition sign in between the logarithms, right? So we can write this as natural log of 5, and then it'd be plus natural log of x. And that is it. That is legitimately it. Later on, we will. I mean, if we are given an equation, again, remember an equation has an equal sign in it, right? When we are given an equation, we will have to solve for x. But right now, we're just moving things around, rewriting what logarithms can look like, and we're just calling it a day there. Okay. So B, we've got log base 2 of 8 times x. Okay. So 8 times x. So we can write this as log base 2 of 8, and then plus log base 2 of x, okay? But we're not done yet, okay? Why are we not done? Because we hopefully can see that there's a relationship here, log base 2 of 8, okay? So if we were to take this and rewrite this in exponential form, 2 raised to, we'll put a question mark, what power is equal to 8, right? That's going just from logarithmic to exponential, okay? Well, 2 raised to what power is equal to 8? Well, it would be 2 cubed, right? 2 cubed is equal to 8. So we can rewrite what's in that box as, what is it, cubed? Yeah, 3. So we can say 3 plus log base 2 of x. Okay, a little extra step there, but it's not abundantly difficult to be able to see that relationship. And again, the relationships that you'll see there are basically just powers of, and relatively low numbers, right? I mean, just off the top of my head, I have no idea what 7 cubed is. So I won't be able to see that relationship if I see it. I won't be able to recognize the relationship if I see it. But like with 2s and 3s, you probably can, and that's honestly as high and as far as it will go. So don't stress too much about that. Let's see, that was a caution there. That's a good one. We'll put this caution on that page. Okay. I don't know where that would have happened here, but just to go over it to be extra thorough, log base b of u plus v is not equivalent to log base b of u plus log base b of v. All right, so we're still expanding. Okay. Alrighty, so we're still expanding. This time we're doing division. Alrighty, so we have log base 5 of 12 divided by x. Okay. Well, the argument 12 divided by x, that's a division sign. So this is obviously going to be a subtraction in between, right? So we're going to say log base 5 of 12 minus log base 5 of x. This light usually isn't on. Is my camera on? Nah, it doesn't matter. Let's look at the sky anyways. Alrighty. And we'll look here. Is there a relationship between 5 and 12? Well, no, not really. So we can just leave that as is. Okay. Next up we have natural log of x and then minus natural log of e to the 5th. Okay. Now, similar to the first problem, we're not necessarily done here, right? Because there's a relationship right here. Okay, and it's that cancellation property, right? Saying the natural log of e, all right, the natural log of e is just 1, all right? So we can rewrite that as a 1. Let's see here. Also, I was trying to think. Okay, so I can't remember the precise example of yeah, it doesn't matter. Okay. What we did do, though, and I forgot that we actually talked about it, was this here, okay, the power rule, okay? If we have that exponent, then we can put that exponent out front. So let's go ahead and do that real quickly for the second part of b, okay? So let's rewrite b. We'll write it like this. And we're going to go ahead and put minus 5 natural log of e, okay? Because, again, we're taking that exponent here and we're putting it out front. Right. Now, if you want to, you can either do it now or pause the video and check it out later. But if you were to put the natural log of e into your calculator, because they are inverses of one another, you will get 1 as your answer. So if you type in the natural log of e, you'll get 1. So this is essentially saying negative 5 times 1. Okay, and of course, 1 times anything is just that anything. So that's why we would simply just write this as the natural log of x minus 5, because Again, the natural log of e is just 1, and then you know, I wouldn't say it cancels, right? Because it exists, it's there. It's just it's 1 and it's redundant to write 1 times anything. So the final solution would be this. I kind of wrote everywhere and spoke everywhere, but that is the final solution. All right, so now we're going to be expanding. No, we're not. Shoot. No, I'm just really wanting to expand right now, guys. All right, so we're going to be using the power rule, which we did on the previous example, but that's fine. All right, so all right, so we have the log. All right, log what? What's it? Since it is simply a that there's no log given, then it's a log base 10. Okay, and I don't know if that's necessarily going to come into play here, but that is the way it is. Okay, and apparently since we're just rewriting this using the power rule, it appears just knowing that that is a base 10 right here. Right, again, the implied base doesn't really matter. Okay, but anyways, if we just rewrite this using the power rule, well, we see the 3 up here is in our exponent. We know we're just going to put it out in front. Okay, we're just going to put that exponent out in front, so it's going to be 3 log 6. That's it. Okay, again, to me, that's so much more fun, isn't it? And then B. Okay, we're not gonna jump straight into writing the solution. Instead, what we're gonna do is we're going to rewrite that radical. Okay, we're gonna rewrite the radical in terms of a fractional exponent. What do I mean by that? Well, we're gonna have log, and then it's a base of 1/2, and then the argument is going to be x raised to the 1/4 power, right? Because that's a root. That's the root of 4, right? And of course we have the implied 1 right here inside. So it'd be 1 over the root, which would be 1/4. Right? And then we know that we can just simply take that exponent, put it out front, and call it a day. Right? So that's the power rule. Maybe we're going to condense now. No, we're still not going to. All right, well, I know we get there eventually. I just forgot when. Alrighty, so use properties of logarithms to evaluate expressions. All right, so A looks like an absolute doozy, okay? But we'll just tackle this, you know, one leg at a time, and then hopefully it should become apparent what it is, okay? So looking at A, let's just go ahead and rewrite it because it's probably really small right now. So let's rewrite this. It is 7 log base 7 of 6 plus log base 7 of 3. Okay, and as I rewrote that, hopefully you saw or noticed that, okay, so we have an addition here, so we can condense. Okay, we can finally do the condensing that we've been promised, right? So by condensing, we know we can write this as 7 and then log and then base 7, and then it becomes, since it's an addition sign here, that means we're going to multiply the 6 and the 3, so 18, right? So it's going to be 7 raised to the log base 7 of 18. Okay. Now it wants us to evaluate this without using a calculator, which, lucky for them, we don't really know how to put this into our calculator just yet. There might be some among you that know how to, but as of right now, I would guess that many of you do not. Okay. So instead, we're going to have to think about this. Okay, so this kind of looks like a problem we had the other day. Okay, or one of the properties we had the other day, and I know that it's the cancellation property, but you probably didn't memorize these properties because, you know, and admittedly they get kind of convoluted. Plus, I did say that you can come up with these properties pretty much on your own by just knowing this part here. Log base x what did we do? Oh no, we did base b. Log base b of x is equal to y, and that means that we can also have b raised to the y power is equal to x. Okay, if you just know that, then you can come up with all those properties that we saw the other day. Okay, so let's go ahead and use that kind of thought process here. Okay, so we have this. This is an exponential form. Okay, so if we were to continue this out, you know, it would be equal to, and again, you know, we put a question mark, right, just to kind of point out why algebra is algebra instead of, you know, question marks. We use x's. All right, so let's just go ahead and use a question mark for now. All right, and let's actually change that color. Let's change it to blue. Okay, all right, and as of right now, it is set up looking like this. It's set up looking like the exponential, right? Because it's, you know, 7 is the base, all this is the y, and my x is the question mark. Okay, so let's change this from exponential, and let's change this to, or let's change this from exponential to logarithmic. Okay, so we're going to say log base what? Looks like base 7. Okay, of, all right, of, well, we don't know because that's the question mark on the other side, right? That's this right here. All right, and that's going to be equal to log base 7. Again, it's equal to the exponent, right? So log base 7 of what is equal to log base 7 of 18? Well, this should be pretty easy, right? I mean, the log base 7s are the exact same. Well, it just looks like the question mark and the 18 are the ones that are in that specific position, right? So it appears that 18 is going to be my solution there. And I'll go ahead and keep that there. And so this means that if we evaluate this equation, then our solution would indeed be 18. Okay, and again, this is from one of the properties that we went over, but I was not a very good student when I was in college, so I feel like I definitely speak from a place of truth there. I didn't memorize the properties, and I did just basically remember. As long as you remember this, you're good to go. Hopefully, okay. But at the same time, we'll say this: you're not gonna have a problem like this on the final exam. You're welcome. But again, once again, the homework will be pretty tough. Okay. So let's go ahead and do B. All right. So B. B looks pretty ridiculous too. Okay, so again, I'm going to rewrite B because it is a little small. I'm not entirely sure if I'm doing it any better or doing it any better for you, but we're trying. This is just a ridiculous problem. Okay, so same as before, what we're going to do is we're going to go ahead and condense everything together. So we're going to end up with, we're going to end up with, let's actually do the power rule first. How about that? Okay, so we're going to end up with natural log of 5 squared, and then we're going to have minus the natural log of, and that's going to be the cube root, no, small 3's are my bane, oh, that worked out, the cube root of 64, because again, what I'm doing is I'm taking this and putting it as an exponent, and being something raised to the 1/3 would be the cube root. Okay, and then we're going to have plus the natural log of 1. Right. All right, so from here, let's go ahead and change this 5 raised to the, or 5 squared. Let's go ahead and change that to 25. Okay, so just so I don't have to write an extra step there. All right, so this again looks absolutely ridiculous, but we're going to take this one step at a time, and we're going to follow along with the condensing that we talked about earlier. Okay, so we're going to have E, and then we have the natural log of 25 minus the natural log of the cube root of 64, which, by the way, I just now realized that, well, the cube root of 64 is actually a number. So we can actually do something with that, okay? So what can we do to that? Well, the cube root of 64 is 4, right? 4 times 4 times 4 is indeed 64. So let's go ahead and put that in for my natural log. Okay. Alrighty. So now what we can do is we can write this as the natural log of 25, and then, oh gosh, okay, divided by 24. Well, that's just something ridiculous. All right, we're gonna have to we're gonna zoom in just a little bit. Okay, we're gonna write this as a big E. All right, so we got a big E, and then we're gonna put a 25. Oh, natural log of 25 over 64. Okay, and then it is a plus the natural log of 1. Okay, so, well, we'll go and put that right now just so people don't get lost here. Okay, so at this point, our problem isn't necessarily done, but it is kind of done, okay? So now how earlier I said, okay, so go ahead and put, the natural log of E into your calculator, and when you do that, you should get a 1. Let me just make sure real quick. Yeah, okay, good. Well, if you put a natural log of 1 into your calculator, okay, if you put a natural log of 1 in your calculator, you should get 0. So this is going to be 0. Okay, so since that is 0, then my final solution is going to end up being e to the natural log of 25 over 64. And I don't think we can do anything with that. Oh, I didn't mean 64. 64 was what was in the radical. The cube root of 64 is 4. Sorry about that. Okay. And I believe that covers it. Yeah, okay. So again, the new thing that we kind of learned here is that the natural log of 1 is equal to 0. Other than that, we just did our power properties there. All right. Now we will expand. Okay, so expanding gets a little sticky. Okay, but it is straightforward, and maybe it's just sticky because of the particular problems that are given to us. But yeah. All right. So starting with A, we're trying to expand here. Okay. So looking here, it looks like we have a 49, and it's times an x cubed, which is times a fifth root of y, okay? So it appears that we have 3 different terms in here that are being multiplied by each other. All right? So what we're going to do is we're just going to write 3 different terms with a log base 7. So I'm going to keep those red blocks there just for a second. So log base 7, okay? And again, we have of 49. All right? And we are multiplying still, so we're going to say log base 7 of x cubed, and still multiplying, and so we're going to say log base 7 of the fifth root of y squared. And let's go ahead and rewrite the fifth root of y squared as y to the 2/5 power. Okay, we went ahead and wrote y to the 2/5 power because, I mean, obviously we're going to be putting this exponent out front, right? So we went and took off the radical, and the fifth root of 2 is the same thing as saying 2 to the 5th power as an exponent, okay? Alrighty, well, cleaning this up a little bit. All right, let's go ahead and erase this now. All right, so cleaning this up a little bit, we should see the relationship here, right? Excuse me. 7 raised to what power is equal to 49? Well, 7 raised to the 2nd power. So this log base 7 of 49 is just simply 2. Okay, so we can rewrite that as 2. All right, And then it appears we can do the power rule here. We can move this 3 out front. So this ends up being plus 3 log base 7 of x. And then similarly, we can move this 2/5 out front here. So this would be plus 2/5 log base 7 of y. All right. And I don't believe there's anything else that we can do to that, so let's go ahead and move to B. All right. So B, looking here, it appears, oh, here we go. Okay, so we have us a, looks like we have us a, well, this is actually a difference of squares, okay, which can turn into an x plus 2, x minus 2. So we need to be able to spot that. We also have a division symbol, which means we're going to have a subtraction sign. But then we also have this 9 being multiplied by the e raised to the x cubed power. Okay, so we have all sorts of stuff in this particular problem. So let's start from the top. Sorry, I gotta sneeze. But anyways, let's go ahead and rewrite this with my numerator having that difference of squares already laid out. So we're going to have the natural log of, and my numerator is going to become x plus 2 x minus 2, that's going to be all over 9e raised to the x cubed. And, okay, so I knew that was just going to be a fail. Let's fix that. E to the x. Okay, maybe that's okay. Yeah, I think it's okay. Okay, so now it becomes pretty apparent here that it appears, okay, so starting off we have us a multiplication right up here, we have the division right here, and we have multiplication right here. Okay, so we've got multiplication and division here. How do we tackle this? Well, it's not difficult, okay, but we have got to be super redundant. And what I mean by super redundant is we're going to have to put a parentheses on the denominator to denote that it is indeed on the denominator. Okay, and I don't even know if what I said made sense, so let's work on this and hopefully that'll make sense. Okay, so here we go. We're going to end up with the natural log of, okay, my numerator. Okay, this is pretty easy. So my numerator is just going to be x plus 2, and then it's going to be plus the natural log of x minus 2. Okay, pretty easy there. Okay, but my denominator, okay, since it's a subtraction, we're going to put minus here, okay? But since there is more than one, let's try to get a straight subtraction sign. What's going on? No, that's fine. Since there is more than one term, okay? And honestly, I'd probably do this even if there was one term, just to be super redundant, all right? But since there's more than one term in my denominator, I'm going to put a bracket here, okay? Because we're going to end up having a natural log of 9 and then plus, and well, no, we'll leave that as that, okay? And then we'll have the natural log of e, oh, okay, maybe we shouldn't have. We'll do that. Okay. Now again, we put those in brackets because this entire term is in the denominator, okay? Had we not put it in brackets, right, we would have said, minus the natural log of 9. Well, and then you'll plus the natural log of e raised to the x cubed. Well, if I were to try and work this, backwards, because right now what we're doing is we're expanding. If I were to condense this particular problem, it would just appear that because we have the minus here only attached to the natural log of 9, then it would appear only the natural log of 9 would be in the denominator. Okay, but that's why we have to put that bracket there to show that this entire problem is indeed, or I'm sorry, this entire right side here is indeed in the denominator. Okay, well, I'm going to do something real quick, just kind of kind of save space, but you know, because I don't think I have to do one more line. No. Okay, so we're just going to try and do something real quick. We're going to look strictly at this, okay? We know that this is natural log of e raised to the x cubed power. So we know that this x cubed comes out in front of the natural log of e, right? So let's go ahead and do that. Let's go ahead and put the x cubed in front of the natural log of e. Like that, okay? Alrighty. Well, next up, we know, and we've shown earlier, that if we take the natural log of e, then we should get 1, right? So this turns into a 1, right? So we can essentially kind of erase that, right? Because 1 times anything is that anything, as we have mentioned before. So we can essentially just erase that. Okay. And then this is the problem we have. And then now if we want to get rid of those brackets, we can now officially rewrite this particular problem. And then we're going to distribute that negative sign, so minus natural log of 9. Distribute that negative sign again, which would be, oh yeah, x cubed. Okay, there is no natural log there because, well, the natural log and e, they canceled. Anyways, that is how we do b. All right, one moment. Alrighty. Man, I'm just, it's pollen. Let's see. Go here. Then we can move on to the next problem. Okay, that's the problem we just did. Alright, so let's condense some more. Alrighty, so right away, let's just jump right into it. We see that we have as a power rule starting off. So let's go ahead and put the 1/2, and let's just go ahead and make it a square root. Actually, I don't know. So the homework actually probably wants it as an exponent. Never mind. So let's go ahead and put that 1/2 onto the x minus 1. So we're going to end up with a log of x minus 1 raised to the 1/2 power. Okay, and then minus log of z cubed, and then plus log 5. Okay, alrighty, well, I've got a subtraction sign and I've got an addition sign here. Okay, so it looks like we're going to have a fraction. It looks like, I mean, just kind of, let's see, I'm going to just try something here. Okay, alright, so to me, the visualization looks like this. This is going to go on top of this, and this is going to go on top of that as well. Alright, that's just the visualization I have in my head, and maybe it popped up in your head too. I don't know, but that's essentially what's going to happen. Okay, because we do indeed have that minus sign, means we're going to have a division. So we're going to end up with a log of x minus 1 raised to the 1/2 power over log of z cubed. Okay, and then that's plus log of 5. Okay, well, plus log of 5, well, that's just going to put, oh shoot, sorry about that. I went a little crazy with my logs there. There we go. And then plus log of 5. Okay. Well, we know this plus log of 5, that plus means that we're going to be multiplying this 5 here times this argument here. Okay, so this turns into, and I'm pretty sure I'll have enough room. Let's see. This turns into log of 5 times x minus 1 raised to the 1/2 power all over z cubed. Okay, and that's it. We did the power rule, and then we did our product. Was it called product rule? Yeah, product rule and quotient rules. We did all those rules put together in A, and presumably we'll probably do it in B as well. Okay, so let's go ahead and do B. Okay. All right, so B, it appears we have the 1/3. Well, doesn't appear. I mean, it definitely is. It's out front in front of the entire problem. Okay. So what we would be tempted to do right away is to put the 1/3 onto these. Okay. And I say tempted to do that because honestly, you might still see what's 1/3. Okay, so forget that. Forget that. Forget what I said. Um, it might work sometimes, it might not work, and so it's not a good rule. So forget it. Okay. Instead, what we're going to do is we're going to stick to rules that we are very familiar with, and that is Pemdas. Okay. So dealing strictly with Pemdas, let's go ahead and rewrite this as, okay. So this is going to be log base 3. Okay. And we have as a fraction sign. I'm sorry, a subtraction sign. So that means that we're going to have a fraction, okay? And I'm going to go ahead and kind of do 2 steps in one here. I'm going to go ahead and move this 2 onto the y, okay? So this will turn into log base 3 of, and then we're going to have x in my numerator, and then in my denominator we're going to have a y squared, okay? So hopefully you see, you catch what I just did there. All I did was went ahead and put the 2 onto the y, all right, to make it a y squared, and then I dealt with that subtraction sign by using the division sign. Okay, all right. So let's do that. I just want to erase the red here. All right, and then that takes care of that. And then outside the parentheses, we're gonna have a log base 3 of 10. And do we see a relationship between log base 3 and a 10? No, 10 and 3 have absolutely nothing in common, so that we're just going to leave that as is for right now. Okay. Well, the next step we're going to do is we're going to deal with that 1/3. Okay. The 1/3 is now going to go in front of, I'm sorry, going from in front of the log, and it's going to be now placed on our arguments. Okay. So we're going to have log base 3, and then it's going to be of x over y squared, and it's going to be raised to the 1/3 power. Okay, so again, we're taking the cube root of those, and this is going to be plus log base 3 of 10. Log base 3 of 10. Alrighty, and lastly, I'm sure we can fit this one in here as well. Okay, so since we have our same bases and we have the addition sign, then we know that we can move this. We're going to be multiplying our arguments together. So we're multiplying this 10 by this argument here. So it's just going to simply be log base 3, and then 10, and this multiplied by x over y squared to the 1/3. Okay, and that does look like a ridiculous solution, but it is what it is. Alright, so next we're going to actually solve logarithmic equations. I believe there's only 2 examples here. Yeah, okay. So we'll go ahead and put this on the next page. All right, here we go. All right, so similar to how when we solved um, exponential equations, okay, we solved exponential equations by, equating the exponents together, right? So, for instance, if we had, some x to the, let's, yeah, some x to the y power, right, and then that's equal to some x to the b power, then we know, or what we did was we said y is equal to b, and then we solved that way. Okay, because since we had the same bases, okay, in this particular case, we had both of them were x. Since we had the same base, then all we had to do is equate the exponent, and of course the exponent, in this particular case was like, let's actually do a better example, one that you might have seen. So we'll say 9 to the x plus 3 power is equal to 9 to the fourth power. Okay, what we did here was we said x plus 3 is equal to 4. We solved for x, so x was equal to 1. Okay, which made sense, right? Because if we put a 1 right here, well, 1 plus 3 is 4. 9 to the fourth is indeed equal to 9 to the fourth. Okay, so that's what we did with exponential functions. We equated the exponents. Well, with logarithmic functions, what we're going to do is we're going to equate the argument. Okay, and again, just drawing our attention here to the logarithm property of equality. All right. So if we have some log base b of u, and that's equal to log base b of v, then all we have to do is equate u and v. All right. And then of course it says furthermore, if u is equal to v, then log base b of u is equal to log base b of v. That's just a statement that can be read forward and backwards. Alrighty. So all we have to do is we have to make sure that the logarithm have the same base. And if they have the same base, then all we have to do is equate the argument. That's it. Okay. So let's look at the example. All right, and an example, or in A, we do indeed see we have the same base, right? We see we have a 7 for a base here and a 7 for a base here. So since we have the same base, we can proceed with our, what do we call it? Our logarithm property of equality. Okay. And actually, the fun part is we don't have to move anything around, right? So at least for this example, all we have to do is say x minus 1 is equal to 12. Okay, and so this means that x is equal to 13. Okay, now I will say this. So far, well, I won't say so far, but throughout the semester, I have mentioned, sometimes, you have got to check your solution, and sometimes you can just go base it off of, well, if I'm right, I'm right. If I'm wrong, whatever. Okay, and I'm of course in the latter group there, right? But I did say there are some problems that you have to check. Okay. Well, when we deal with logarithms, we have to check. All right, and we won't see it in this example, but we will see it in the next example. Right. So anyways, if we plug in a 13 here for x, we see that 13 minus 1 is indeed 12, and log base 7 of 12 is equal to log base 7 of 12. So we're in the clear there. But I'm pretty sure B is not going to be as happy about it, and we'll see what happens. Okay. So we have 2 natural log of x is equal to a natural log of 16. Okay. Well, we obviously have the same base, but this 2 out in front kind of ruins things a little bit, right? Well, lucky for us, we have our power rule, so we can rewrite this as the natural log, fix that L, the natural log of x squared, and that's going to be equal to the natural log of 16. Okay, well now we have the same argument, okay, so my arguments here is x squared and 16. Alrighty, so since we have the same argument, we can now equate those two together. So we're going to have x squared is equal to 16. And this is a pretty easy one to do, right? We've got x is equal to plus or minus 4. Okay. Well, as I said, we have to plug these in. Right. So we're going to plug this in. So if we plug in a positive 4 into our equation over here. Okay, well, 2 natural log 4, that's fine. Natural log of 4 is an actual number. We're good to go. So positive 4 works. Okay, and of course, with that said, negative 4 will not work. okay? Because the natural log of -4, well, that doesn't exist, okay? Because negative numbers are not in the domain of logarithms, okay? Remember how our graph looked? It looked like this, right? And then here on the x-axis, we see that my graph does not exist anywhere to the negative numbers. So we know that the domain of our logarithms cannot be a negative number. So therefore, -4 will not be a solution. Let's see, we'll just put a little green arrow, and we'll say x is equal to 4. Okay. We'll mark out the negative here. Okay. Now, you might be thinking, well, that seems pretty easy. Like, why would I have to check it? Because it appears, if I put a negative number in there, then it'll work. Or I'm sorry, it won't work, right? So you could probably just think, okay, well, as long as my solution is a negative, it'll work. What sucks is for this particular section, and I don't know if it actually gets any harder. I also teach pre-calculus algebra, and realistically, they're pretty much the same class, except we go over something a little bit different in pre-cal algebra. But we have went over these logarithms, and I can't remember if it was this class or that class. But the solutions of the logarithms are played with a little bit more in one or the other, and it might be the other class. But with that said, let's look at if a problem was log of x. I don't know. No, let's do 4 minus x. Okay. No, let's do 3 minus x. Make it easier. 3 minus x. Okay. All right. So if we had log 3 minus x, and this is just some arbitrary problem. Okay, some arbitrary problem, and we got the solution x is equal to positive and -4. Okay. Well, in this particular case, the +4 would not be the solution, and the -4 would be. Why? Well, here's why. If we plugged in a +4 here, well, 3 minus 4 is a -1, and the log of -1 does not exist. Okay. However, if we took 3 minus a negative, well, let's do this. If we did 3 minus a -4, okay, well, that's the same thing as saying 3 plus 4, which is 7, and that the log of 7 does exist. Okay, so you have to be a little careful there as to make these quick rules in your head, saying, okay, well, if my solution is negative, and in this particular case we have a negative solution, then it would not be part of the solution. That is not always the case at all, and don't make that mistake. Okay, so when I said that when we check our solutions with logarithms, full stop, we have to check our solutions. Okay, it's not going to be one of those things where you do the algebra. If you're right, you're right. If you're wrong, you're wrong. You have to check your solution. Okay, so hopefully that example helped out. I don't know if it did or not. Maybe my thing's worse. That is the name of the game. That's what I do. I'm sorry. And that was B, right? Yeah, we did A and B there. Okay, cool. Alrighty, so next up we're going to talk about the change of base. Okay, so changing the base is useful for whenever you have two logarithms, and well they have different bases. Okay, because everything that we've done so far only works when we have the same base, right? For instance, this particular problem here, we can only solve this particular problem because in both sides we have a log base 7. Okay. Well, what happens if this is a log base 8? It's a horrible looking 8, but what if this was a log base 8? Okay. Well, then right off the bat, okay, right out of the gate, we can't necessarily solve it. Okay, because well they have different bases, and by having different bases, we cannot do our logarithm property of equality because this requires the bases to be the same. Okay, so that's why we use the change of base formula. And the change of base formula is super duper simple. Super duper simple, okay? Um, if you want to change the base of some number, okay, so or some logarithm, so this particular logarithm has a base of b, right? It's log base b, so it has a base of b. If I want to change it to some number, any number, and in this example, that number would be a, okay? So we're changing it from a b to an a. Then all you have to do is change it from or do log base a of the argument, right? So in this particular case, it would be u, over the log base a of the old base, which is b. Okay, so hopefully you can see that, and then of course if you want to see how the numbers play out here, this is how it plays out. So it appears for this example we're trying to change from a log base 3, okay, so from a log base 3 to a log base 7. Okay, all you have to do is say, okay, well, I want a base of 7 now. So you would say log base 7 of the old argument, which is 10, okay, and then log base 7 of the old base, which is 3. And that's it. That's it. That's all you have to do. And I don't know if it says it here. Okay, good. It does. I wonder if I can fit that in there. We'll just give it its own page. Okay. You could use either log or natural log. It does not matter. Okay. Because it will be the same either way. So in this particular case, if we changed we're going to change log base 3 of 10, we want to change it into a base of 10. Okay, so and again, base 10 is your default log, right? So you would just say log of 10, which is the old argument, over the log of 3, which is the old base, and you would get 2.0959. Well, if you want to do that with natural log, you can, right? And you will get the exact same answer, the exact same solution. Okay. So I say that because I just use, I mean, unless I just have to use, a log of a certain base, which we will see as the last example today, I would generally just use the natural log to evaluate some sort of logarithm. And I'll show you what I mean here. Okay. Alrighty, so change of base is not only useful to change a base into a base that you want that is a lot easier to deal with algebraically, but also because I don't know about you guys, and let me make double sure here. If I click the log button on my calculator, okay, I can't change my base. Okay, my base is in 10. Now I'm not saying that your calculator couldn't do it. Okay, but on my calculator and on many calculators, the only log you can do is log base 10, and of course it just says log. The base 10 again is implied, so you can't do you can't necessarily put this into your calculator. Right now, again, if you can put this in your calculator, good job. You have a really nice calculator, I guess. But for most of you, you cannot put log base 9 into your calculator. You cannot change the base there. Okay. So what we'll have to do is we'll have to do the change of base. So all we have to do to figure out what log base 9 of 200 is just simply say natural log of 200 over the natural log of 9, okay, and of course that is equal to the log of 200 over the log of 9, which is going to be equal to 2 to 4 decimal places, so 2.4114. Okay. And that's it. That is change of base. Okay. And again, we're doing that in this particular case because, well, we don't have a base 9 in our calculator. Okay. And if you don't have a base 9 in your calculator, I bet you don't have a base square root of 3, right? So all we have to do is again put this into our calculator as, okay. And again, I always do natural log of things instead of log. And again, as you can see, they are the exact same. Okay. I always do natural log because, and this would be for those of you that are going into higher mathematics. We use natural log a lot more whenever we get to differential equations, and it just becomes a habit of something that I and many of my colleagues also do more. Okay, but again, they will indeed equal the same thing, so it doesn't matter. Natural log of pi divided by natural log of square root of 3. It's 2.0839, which would be 4. Okay. And that is the change of base. That's how we do change of base whenever we're trying to evaluate some expression into a number into some hardcore number. Okay, so instead of writing the natural log of whatever over whatever. Okay, and then of course, and as I mentioned, the last reason why we would need to change base is because of a problem like this. Okay, so this reads: use the change of base formula and the properties of logarithms to rewrite as a single logarithm involving base 2. Okay, so in order to write it as a single logarithm involving base 2, okay, this is basically what we started the entire lecture out on. Okay, which was condensing and expanding, right? In this particular case, it wants us to condense this equation into one simple equation, but with a base of 2. Well, we've done that a lot so far in today's lecture, but in those cases, our bases were the same. Okay, well, in this particular problem, our bases are not the same, so therefore we must make them the same, right? So in order to do that, we need to do the change of base. Okay, well, let's go ahead and change the base of the because it wants us in base 2. So, well, this is already in base 2, so that's good to go. We don't have to do anything with that. This is in base 4, we must change that base. Okay, so in order to change the base, we're going to write log of, and then it's going to be, oh yes, log base 2, sorry. Log base 2 of the old argument, which is x, over log base 2 of the old base, which is 4. Okay, and that's plus, and let's go ahead and put that 3 onto that y, so we're going to say log base 2 of y cubed. Okay, alrighty, well, log base 2 of 4, that's pretty easy, right? I mean, 2 raised to what power is equal to 4? Well, that's going to be 2. Okay, so let's go ahead and change that now to, we're going to change the denominator to simply a 2, so log base 2 of x over 2, and then that's plus log base 2 of y cubed. Okay, and maybe I could have written a little bit smaller. Oh well. Alrighty, so oh, this is actually pretty interesting. Okay, so we have log base 2 of x over 2, and how do we deal with that 2 in the denominator? Okay, well, in order to deal with that 2, what we're going to have to do is we're going to have to move that 2 out front. So let's go ahead and snip this. Let's see. Is this the way to do it? Yeah, okay. No, that's not it. Oh, it's this button, Sherman. Okay, let's just put this on the next page real quick. Okay, so we know that we can rewrite this as 1/2, right? Because it's 2. It's that logarithm over 2, so I can say 1/2 log base 2 of x, and then plus log base 2 of y cubed, right? Okay, and then that makes it pretty simple to see that, okay, well, that 1/2 is going to go onto that x, right? So we're going to have log base 2 of x to the 1/2 power plus log base 2 of y cubed, right? And then lastly, we know that we can simply multiply my arguments together now, right? Because we have the same base. So we can multiply our arguments together. We can say log base 2 of, let's put y first. Y cubed times x to the 1/2. Okay? And that's it. That is, we took the problem with a base of 4, and then we changed it to a base of 2, and then condensed this particular problem into one problem with a base of 2. Okay. All right, and that does conclude today's lecture.